This video is a supplementary learning material to accompany the self-learning module titled Ionic and Covalent Bonding, together with Teacher Jackie and Teacher Dan.
Hi there again! Nice to see you back! Remember the video about how ionic bonds are formed? That was the first video of this 3-part series. Now, we're on our second video, and this time, we are going to talk about how covalent bonds are formed. So, ionic out, covalent in. We're now moving on to covalent compounds and their covalent bonds. Our substance in focus? Fluorine monofluoride, a compound made of the elements fluorine and chlorine, which are both nonmetals. Fluorine monofluoride is a covalent compound, which means that the atoms are held by covalent bonds. But the question now is, how exactly does covalent bond form between atoms? To answer that, we need to take a closer look at their electrons. We can see here that chlorine and fluorine belong to the same group, which means that these atoms have the same number of valence electrons.
This is shown in these representations of chlorine atom and fluorine atom. Both of them have 7 valence electrons. Now, what can you say about this number? Does it follow the octet rule?
7 is a very close number to 8, which means that chlorine and fluorine are both 1 valence electron away from achieving octet. And because they're so close to achieving their dreams, neither of them wants to give up an electron. So how do you think these two atoms cooperate to achieve octet?
Instead of transferring electrons, chlorine and fluorine will share 2 electrons between them. This sharing of electrons effectively allows both atoms to achieve octet. Notice how the valence shells of both atoms overlap. That is the reason why we call it covalent. The overlapping of valence shells allows the sharing of electrons. The attraction between the shared pair of electrons, which are negatively charged, and the nuclei of the bonding atoms, which are positively charged, brings about the binding force in a covalent compound. In fact, that is how all covalent bonds are formed. In the first part of this video series, sucrose and octadecane are the covalent compounds. These substances are composed of covalently bonded atoms. These are the molecular representations of those compounds. See those green and red lines between the element symbols? Those are representations of the covalent bonds between atoms.
All covalent bonds are formed this way. It is all a matter of sharing of electrons between the atoms to attain that 8 valence electrons. So, to sum it up, covalent bond involves sharing of electrons. I hope you still remember that when it comes with ionic bonds, it involves transfer of electrons. Now, there's another thing that we need to note about covalent bonds. The degree of sharing of the bonding electrons varies. The sharing of electrons may be equal or not. It all depends on the atom's tendency to pull electrons toward themselves. We refer to this as electronegativity. Let's look at these illustrations to understand how electronegativity affects the sharing of electrons. If 2 bonded atoms have equal values of electronegativity, then they will have an equal pull on the shared electrons between them. In short, equal sharing of electrons.
However, if one atom has higher electronegativity than the other, then the electrons will not be shared equally between them. In this example, the shared electrons will tend to move around chlorine to a greater extent.
Now, you might be asking, why is this important? Remember that electrons are negatively charged particles. If they spend most of their time moving around a chlorine atom, this will affect the partial relative charges of the atoms in the bond. The more electronegative atom will carry a partial negative charge, and this leaves the less electronegative atom with a partial positive charge. Now, we have a covalent bond with opposite partial charges. Any guess what we call this kind of bond? Here's a clue. Think of poles. Covalent bonds exhibiting opposite partial charges are called polar covalent bonds, or simply polar bonds.
There is also a term used for covalent bonds with equal sharing of electrons. We call them nonpolar covalent bonds, or simply nonpolar bonds. Nonpolar bonds do not have opposite poles. However, keep in mind that electrons are continuously moving. Because of this, there are instances that electrons may be moving in one atom more than the other. This creates an instantaneous charge. As the word instantaneous suggests, this only happens at an instant. Thus, it is only a temporary charge. Atoms, then, in nonpolar bonds essentially have no charge relative to polar bonds.
So, electronegativity affects the sharing of electrons. But how exactly do we determine the electronegativities of different atoms? Well, somebody did that for us, thanks to this guy, Linus Pauling.
While there are several scientists who developed scales of electronegativities, the one with the simplest values was that of Pauling's.
And the range of that scale is large, from 0 to 4. That big. That is why a difference in electronegativity of 1.9 is already large. By the way, the highest value in that scale, 4, is for the most electronegative atom, the fluorine atom.
It's quite handy to know about this scale because the difference in electronegativity values of two atoms determines the polarity of the bond that they will form. If the difference is less than or equal to 0.4, then the bond is considered as nonpolar covalent. If it is between 0.4 and 1.9, then the bond is considered as polar covalent. Now, what do you think happens if the electronegativity difference is equal or greater than 1.9? See, that's a very huge difference in electronegativity values of two atoms. Usually, it occurs between a metal and a non-metal. Do you see where I'm getting at? In situations of large electronegativity differences, the attraction of the electronegative atom must be very strong, causing a complete transfer of shared electrons. This eventually results in ionic bonding.
And why is it important to know bond polarities? The polarity of the bond determines the overall polarity of things. In this grade level, you must recognize that covalent bonding forms molecules and that molecules may be polar or nonpolar. Remember that polar molecules carry partial charges. On the other hand, nonpolar molecules do not carry partial charges. In the samples that we used in the activity,
sucrose is an example of a polar molecule, while octadecane is an example of a nonpolar molecule. So far, we have seen three types of chemical bonds: ionic bond, polar covalent bond and nonpolar covalent bond. Note that in an ionic bond, for example in sodium chloride, a complete transfer of electrons is involved. This results in the formation of ions, wherein each has a full charge. In a polar covalent bond, like in a hydrogen chloride molecule, transfer of electrons is only partial. This results in the formation of partial charges in the bonded atoms. Finally, in a nonpolar covalent bond, like in a chlorine molecule, there is no transfer of electrons. Thus, there is essentially zero charge for atoms involved in nonpolar bonding, only instantaneous charges.
This difference in the charge distribution between atoms for each type of bond contributes to the physical properties that substances exhibit. Good job! You have learned now how ionic and covalent bonds are formed. But how will you recognize these compounds based on their properties? Let's find the answer together in part 3 of this video series. I hope you enjoyed watching this video. See you later!